Now let's look at the limit imposed by cutoff. Now what is cutoff? Cutoff is when the transistor drain current falls to 0. Okay. So to avoid cutoff, we must make sure that the total drain current is more than 0. And what is that? The total drain current is ID naught plus GMVI must be more than 0, or VI should be more than minus ID naught by GM. Okay. Now this limit also makes sense. First of all, this is a negative number. Okay. There is some quiescent current in the transistor, and when there is a negative input, the gate voltage falls below the operating point voltage and it tends to move towards cutoff. So it makes sense that this is negative. Okay. So this will give us some value. Now you can also think of cutoff as VGS falling below the threshold voltage. Okay. That is, to avoid cutoff, VGS total has to be greater than the threshold voltage. And what is VGS total? VGS 0 plus VI should be greater than the threshold voltage, or VI should be greater than minus VGS 0 minus VT. Okay. So this is a limit that we get from, this is the limit that we get by applying the cutoff condition by saying that VGS has to be more than the threshold voltage VT. Okay. So we have two different ways of calculating the cutoff limit. But let's go back to this. Now we also know that what is the GM of the transistor? One of the expressions for the GM of the transistor is 2 times ID0 by VGS minus VT. VGS 0 minus VT. The 0 indicates that it's the operating point condition. So if I substitute it in there, what will I get? I'll get that VI should be greater than ID0, which is this, divided by this whole thing, which is minus VGS 0 minus the threshold voltage divided by 2. Okay. Now this, it has VGS 0 minus VT just like this one, but there is an extra factor of 2. Okay. So first, please understand what we are doing. We evaluated the cutoff limit in two different ways. In this case, we have imposed the condition that the total drain current has to be more than 0, and in this case we have imposed the condition that the total gate source voltage has to be more than the threshold voltage, and the two give different answers. Why is that? The actual ID VGS characteristics of the MOS transistor in saturation region is square law. This we know, right? Okay. And for our particular transistor, the current is 0 up to a gate source voltage of 1 volt, and it increases like that. Okay. Right. At 3 volt gate source voltage, we have 200 microamperes. At 2 volts, we have 50 microamperes, and at 4 volts, we have 450 microamperes. Okay. And our operating point is over there. The quiescent gate source voltage is 3 volts, and on top of that we have an increment. What we are saying is that the total gate source voltage, which is 3 volts plus the increment, it will fall below 3 volts when VI is negative. Okay. So 3 plus VI will be anywhere depending on the value of VI, and when it becomes negative, it can reach this point and the current can become 0. So that's the limit that we get by saying that So you can see that this is an increment of minus 2 volts, and this is the limit we get by saying that the total VGS has to be greater than the threshold voltage. Okay. Now we evaluated another limit by saying that ID total has to be greater than 0. The point is, in ID total we had the quiescent current ID0, which is here in our case, plus the incremental drain current was calculated from the small signal equivalent circuit. Okay. So plus Gm times VGS or plus Gm times Vi. In other words, when we say that the total drain current is this, we are really using the tangent to this curve at the operating point. Okay. So we are using the tangent to this curve, and when we say that the total drain current is more than 0, okay, we are utilizing this tangent and looking at where the tangent goes to 0, not where the original ID/VDS curve goes to 0. Okay. So the limit that we get by saying that the total drain current should be more than 0 is this much. Okay, and you can see that this is VGS 0. So this corresponds to an increment of minus 1 volt, and it's exactly half of this. And it's the nature of the parabola that, so where the tangent crosses 0 is exactly halfway to where the parabola actually reaches 0. Okay. So we have evaluated the cutoff limit by using two different criteria. One is by equating the gate source voltage to the threshold voltage, the other by equating the drain current to 0, and these two give different answers. Okay. Now it so happens that most of the time we use this as the limit, that is, we use the total drain current to be more than 0. Okay. There are a couple of reasons for this. Although we know that the actual drain current goes to 0 here, we use this. First of all, this gives you a conservative limit, and as I described earlier, the swing limit is only a crude estimate of how much signal you can apply. Okay. In a real circuit, you have to simulate the circuit, see exactly how much the strength of the harmonics or other distortion products are, and then evaluate your signal limit. Here we just want a crude estimate of the largest signal. Okay. The limit based on the drain current is more conservative, that is, it gives you a smaller limit compared to the limit based on VGS. So that's one thing. And also it turns out that in case of a MOS transistor, we can use either of these conditions. Okay. Whereas in case of a bipolar transistor, the condition based on the total current is really what is usable. Okay. And to use the same method for both circuits with MOS transistors and bipolar transistors, we use the limit based on the total current. Okay. This can be confusing, but I have told you why the two limits are different. In one case we are using the parabola, the other case we are using the tangent line at the operating point. Obviously the tangent line crosses 0 at a different point compared to where the parabola reaches 0, but we still use the tangent line, although it is approximate, because first of all we want only a crude limit, and exactly the same method can be used with bipolar transistors. Okay. Now if we do it for our particular circuit, what do we get? First, the triode region limit. When I say triode region limit, this inequality is written so that the transistor remains in saturation region. It is in saturation region if Vi is less than or equal to VDS 0 minus VGS 0 plus the threshold voltage divided by 1 plus the gain Gm times Rd parallel RL. Okay. And how much is this? VDS 0 is 4 volts, VGS 0 is 3 volts, Vt is 1 volt divided by 1 plus gain, 1 plus this product Gm times Rd parallel RL, which is 5. Okay. So it says that Vi should be less than or equal to, this is 2 volts, 2 by 6 or 1 by 3 volts. So if the input voltage is greater than about 330 millivolts, the transistor will go into triode region. And the cutoff limit, if you use the drain current criterion, we know that Vi should be greater than or equal to minus ID0 by Gm or minus 200 microamperes by 200 microsiemens, which is minus 1 volts. Okay. And if you use the VGS based limit, Vi should be greater than or equal to minus VGS 0 minus VT. VGS 0 is 3 volts, VT is 1 volt. So this says that it is minus 2 volts. Okay. And like I described earlier, this gives us a conservative limit, and this method can also be used with bipolar transistors. So we will use this one. So what this whole exercise is saying is that if Vi is between minus 1 volt and plus 1 by 3 volts, the transistor remains in the desired region of operation and everything works properly. Okay. But if it goes beyond these limits, then the transistor will either enter the triode region or the cutoff region. Okay. So this gives us a crude estimate of how large a signal we can apply. We know that our devices are nonlinear. If you apply an indefinitely large signal to a circuit that contains transistors, you will have very large nonlinear products and the circuit will be unusable. So we want an estimate of how much signal can be applied, and this gives us a crude estimate that doesn't depend on criteria like distortion, which is much harder to evaluate and nearly impossible to do by hand. Okay, you use a circuit simulator for that one. Okay, so to go back to our circuit, so in this circuit, Vi should be less than 1/3 volts and greater than minus 1 volt. Okay, and let's say Vi is a sinusoid. Vi is Vp cos omega t. Now this is a symmetrical waveform, that is, it goes equally in the positive and negative direction. Then what is the largest amplitude that can be applied? Obviously it will be smaller of the two limits, because if you apply an input with an amplitude of 1 by 3 volts, then at the peak of the sinusoid, this limit will be reached. Of course, if you apply an input with an amplitude of 1 volt, it will cross this limit on the positive side. Okay, and the transistor will go into triode region. The smaller of these two limits will decide the amplitude of the sinusoid that can be applied, and in this particular circuit, it's the limit due to the transistor entering triode region that limits the signal swing. Okay, so for this to behave like an amplifier, and we'll say that for it to behave like a linear amplifier, Vp has to be smaller than 1/3 volts. Okay, so I hope this is clear. What we do is calculate the total quantities everywhere, that is VDS, VGS and the drain current ID, and we impose the limits of going into saturation or cutoff. And in case of the cutoff limit, there are two possibilities: to either set the drain current to 0 or the gate source voltage to 0. In our case, we will uniformly use the limit imposed by the drain current. We know that it's only approximate, but we are first of all looking only for a crude estimate, and we also want to use the same method for MOS transistor circuits and bipolar transistor circuits. Okay.